Welcome to this comprehensive guide on measurement error in research and science. Every measurement in science contains some degree of uncertainty. Today we'll learn how to quantify, report, and understand these errors. Let's start by understanding what measurement error actually means. Measurement error is simply the difference between what we measure and the actual true value of a quantity. Mathematically, error equals the measured value minus the true value. Here we see a visual representation. The green dot is the true value, the pink dot is what we measured, and the yellow arrow shows the error between them. Here's an important question. Can we ever know the true value perfectly? The answer is usually no. In most cases, we cannot know the true value perfectly, which is exactly why we need to report our measurement uncertainty. There are two main types of measurement errors we need to understand. Systematic errors are consistent biases that push measurements in one direction. They're like a scale that's always off by the same amount. In systematic error, all measurements are shifted away from the true value in the same direction. Systematic errors come from calibration problems, environmental conditions like temperature or inherent instrument bias. Random errors are unpredictable fluctuations that scatter measurements around the true value. Random errors create a scatter pattern around the true value. Notice how the measurements are distributed randomly in all directions. Random errors come from reading fluctuations, environmental noise, and limitations in human precision when taking measurements. Now let's distinguish between absolute and relative error. Absolute error is the magnitude of the difference between measured and true values. For example, if we measure a 10-centimeter rod as 10.2 centimeters, the absolute error is the magnitude of 10.2 minus 10.0, which equals 0.2 centimeters. Relative error is the absolute error divided by the true value, giving us a fractional measure. In our example, the relative error is 0.2 divided by 10.0, which equals 0.02 or 2%. Here's a good question. Which is more meaningful, absolute error or relative error? The answer depends on context. Relative error is often more useful because it allows us to compare measurements of different magnitudes. Two crucial statistical measures for quantifying uncertainty are standard deviation and standard error. Standard deviation, denoted sigma, is the square root of the average squared deviation from the mean. It measures the spread of individual measurements. Standard deviation tells us how spread out our individual measurements are from the average value. Standard error equals standard deviation divided by the square root of n, where n is the number of measurements. Standard error tells us the uncertainty in our calculated mean value. It gets smaller as we take more measurements. This bell curve shows a normal distribution of measurements. The arrows indicate the standard deviation, showing how wide the distribution is. Let's work through a complete practical example measuring a table length. Suppose we measure a table 5 times and get the following values in centimeters: 150.2, 150.5, 149.8, 150.1, and 150.3. Step 1. Calculate the mean by summing all measurements and dividing by n. The mean equals 150.2 plus 150.5 plus 149.8 plus 150.1 plus 150.3, all divided by 5, giving us 150.18 centimeters. Step 2. Calculate how much each measurement deviates from the mean. The deviations are 0.02, 0.32, negative 0.38, negative 0.08, and 0.12 centimeters. Step 3. Square each deviation, then calculate their average. This gives us a standard deviation of 0.253 centimeters. The standard error equals 0.253 divided by the square root of 5, which is 0.113 centimeters. Our final result is 150.2 plus or minus 0.1 centimeters, where we've rounded appropriately. When we calculate with measured values, errors propagate through our calculations. Here's a practical question. If we measure length and width with errors, what's the error in the calculated area? For addition or subtraction, the combined error is the square root of the sum of squared individual errors. For multiplication, we use relative errors. The relative error in the product is the square root of the sum of squared relative errors. Let's use an example. Length is 10.0 plus or minus 0.2 centimeters, and width is 5.0 plus or minus 0.1 centimeters. The area equals length times width, which is 10.0 times 5.0, giving us 50.0 square centimeters. The relative error in area is the square root of 0.2 over 10.0 squared, plus 0.1 over 5.0 squared, which equals 0.0283. Converting to absolute error, 0.0283 times 50.0 equals 1.4 square centimeters. So our final result is an area of 50.0 plus or minus 1.4 square centimeters. Error bars are visual representations of uncertainty on graphs and charts. Error bars are the vertical or horizontal lines extending from data points that show the range of uncertainty in our measurements. Error bars typically represent either standard error or confidence intervals, depending on what we want to communicate. They're crucial for assessing whether differences between experimental groups are statistically significant or just due to random variation. Let's learn the step-by-step process for calculating and adding error bars to your data. Step 1. For each data point, collect multiple measurements to assess variability. Step 2. Calculate the mean and standard error for each set of measurements. Compute the mean x-bar and standard error, which is sigma divided by square root of n. Step 3. Choose your confidence level. Most scientists use 95% confidence intervals. For 95% confidence, the interval is the mean plus or minus 1.96 times the standard error. Step 4. Plot your mean values as points and add vertical bars extending plus and minus the standard error. Here's a properly formatted graph with error bars. Notice how the bars extend symmetrically above and below each data point, with caps at the ends. Understanding how to interpret error bars is crucial for data analysis. When error bars from two groups overlap substantially, this suggests there's no statistically significant difference between them. Here we see two groups with overlapping error bars. This overlap suggests the difference between groups is likely not statistically significant. When error bars don't overlap, this suggests there might be a significant difference, though statistical tests are needed to confirm. In this case, the error bars don't overlap at all, suggesting a likely significant difference between the groups. Important question. Do non-overlapping error bars guarantee statistical significance? Answer. No, they don't guarantee it. You still need to perform proper statistical tests to confirm significance. Error bars are powerful tools, but they have important limitations we must understand. Limitation 1. Error bars only show summary statistics. They don't reveal the full shape of your data distribution. These two datasets have similar error bars, but notice how the actual data distributions are completely different. Error bars miss this detail. Limitation 2. Error bars calculated from standard deviation are susceptible to outliers that can inflate the apparent uncertainty. Limitation 3. Standard confidence intervals assume your data follows a normal distribution, which isn't always true. Limitation 4. While helpful, error bars don't directly indicate statistical significance. You need actual hypothesis tests. Limitation 5. Error bars can represent standard deviation, standard error, or confidence intervals. Always label what they show. Let's review best practices for reporting measurement errors in scientific work. Best practice 1. Always explicitly state what your error bars represent in figure captions and legends. Best practice 2. Report the number of measurements used to calculate your errors. Best practice 3. Use consistent significant figures. The uncertainty should guide how many digits to report. For example, reporting 23.456 plus or minus 0.123 is correct because the precision matches. But reporting 23.456789 plus or minus 0.1 is wrong because we're claiming more precision than our uncertainty allows. Best practice 4. Always include units for both measurements and errors. Best practice 5. When possible, show both error bars and individual raw data points to give readers full context. Let's summarize with a complete practical workflow. Here's a complete workflow for handling errors in a typical experiment. Step 1 in design. Plan to take multiple measurements for each experimental condition. Step 2. Collect and record all measurements carefully and systematically. Step 3. Calculate the mean and standard error for each set of measurements. Step 4. Create graphs with your data points and appropriate error bars. Step 5. Perform proper statistical tests to assess significance. Step 6. Report your results clearly, stating all uncertainties and the methods you used. This flowchart shows the complete process from experimental design through to final reporting of results with uncertainties. Let's review the key takeaways from this comprehensive guide. Key point 1. Every measurement in science contains some degree of uncertainty that must be quantified. Key point 2. Standard error decreases as you take more measurements, following 1 over square root of n. Key point 3. Error bars are helpful visual tools for assessing variability, but they're not substitutes for proper statistical tests. Key point 4. Always clearly report what your error bars represent in your figures and text. Key point 5. When you calculate with measured values, errors propagate according to specific mathematical rules. Key point 6. Understanding the limitations of error analysis is just as important as knowing how to calculate errors. Measurement science connects precision, accuracy, error, uncertainty, statistics, and analysis into a coherent framework for understanding our experimental results. One final thought to conclude our comprehensive guide. Error analysis is not about finding mistakes in your work. Rather, it's about honestly characterizing the limits of our knowledge and the precision of our measurements. This intellectual honesty in reporting uncertainty is fundamental to the scientific method and maintaining the integrity of research. Science equals measurement plus uncertainty plus honesty. All three components are essential.